Hello everyone, in today's video we'll be discussing on vector calculus. Here is the content of the topics on which we'll be discussing the video. Firstly, we'll discuss about introduction to vector differentiation, followed by scalar and vector fields, gradient and directional derivative, curl and divergence, applications of vector differentiation, and finally the conclusion. Introduction to vector differentiation. Vector differentiation is a fundamental concept in mathematics that plays a crucial role in various fields such as physics, engineering, and computer science. At its core, vector differentiation involves the process of determining how a vector field changes at different points in space. This process is crucial for understanding the behavior of physical systems and for developing mathematical models to describe them. Scalar and vector fields. In mathematics, a scalar field is a function that assigns a scalar value to each point in space. Examples of scalar fields include temperature, pressure, and density. On the other hand, a vector field is a function that assigns a vector to each point in space. Examples of vector fields include velocity, force, and electric field. Gradient and directional derivative. The gradient of a vector field is a mathematical operation that describes the rate of change of the field values at any given point. It is represented as a vector pointing in the direction of the greatest increase in the field, and its magnitude represents the steepness of the increase. The directional derivative of a vector field is a measure of the rate of change of the field in a particular direction. It is calculated by taking the dot product of the gradient with the unit vector in the desired direction. This gives the rate of change of the field per unit length in that direction. Curl and divergence. Curl and divergence are two important concepts in vector differentiation. Curl measures the tendency of a vector field to rotate around a point, while divergence measures the tendency of a vector field to flow away from or towards a point. In other words, curl measures the local rotational behavior of the vector field, while divergence measures the local expansion or contraction of the vector field. Solenoidal and irrotational vector fields are two special types of vector fields that have unique properties with respect to curl and divergence. Solenoidal vector fields have zero divergence and non-zero curl, while irrotational vector fields have zero curl and satisfy Laplace's equation. These properties make solenoidal and irrotational vector fields useful in various applications such as fluid dynamics and electromagnetism. Applications of vector differentiation. Fluid dynamics is a prime example of where vector differentiation is used. By calculating the velocity and pressure gradients of a fluid, we can predict its behavior and make informed decisions about how to control it. For instance, understanding vector differentiation helps us design more efficient airplane wings, reduce drag on ships, and optimize the flow of oil through pipelines. Another field where vector differentiation plays a crucial role is electromagnetism. By calculating the electric and magnetic fields in space, we can determine how charged particles will behave and design devices like motors and generators that rely on these principles. Vector differentiation also helps us to understand the behavior of electromagnetic waves, which are used in everything from radio communication to medical imaging. Coming to the conclusion, in summary, vector differentiation is a fundamental concept in mathematics that involves the study of scalar and vector fields, as well as their derivatives such as gradient, curl, and divergence. It has numerous real-world applications in fields such as fluid dynamics and electromagnetism. By understanding vector differentiation, we can gain a deeper insight into the behavior of physical systems and make accurate predictions about their future states. Therefore, it is an essential tool for scientists and engineers alike. Thank you.